Hello students, in the previous session we introduced ourselves to the concept derivatives. Let us define a derivative. Suppose f is a real valued function and a is a point in its domain of definition. The derivative of f at a is defined by limit f of a plus h minus f of a upon h as h tends to 0, provided this limit exists. Derivative of f of x at a is denoted by f dash a. Observe that f dash a quantifies the change in f of x at a with respect to x. Now, let us solve an example. Find the derivative at x is equal to 2 of the function f of x is equal to 3x. Look at the solution. We have f dash 2 is equal to limit f of 2 plus h minus f of 2 upon h as h tends to 0, that is equal to limit 3 into 2 plus h minus 3 into 2 upon h as h tends to 0, that can be written as limit 6 plus 3h minus 6 upon h as h tends to 0 can be simplified as limit 3h upon h as h tends to 0. That means, it is limit 3 as h tends to 0 is equal to 3. The derivative of the function 3x at x is equal to 2 is 3. Here is an important remark for you. At this stage, please note that evaluating derivative at a point involves effective use of various rules. Limits are subjected to. The following example illustrates this. Find the derivative of sin x at x is equal to 0. Look here, let f of x is equal to sin x, then f dash 0 is equal to limit f of 0 plus h minus f of 0 upon h as h tends to 0 can be written as limit sin 0 plus h minus sin 0 upon h as h tends to 0 can be simplified as limit sin h upon h as h tends to 0 is equal to 1. Let us look into one more example. Find the derivative of f of x is equal to 3 at x is equal to 0 and at x is equal to 3. For the solution, since the derivative measures the change in function, intuitively it is clear that the derivative of the constant function must be 0 at every point. This is indeed supported by the following computation. F dash 0 is equal to limit f of 0 plus h minus f of 0 divided by h as h tends to 0 can be simplified as limit 3 minus 3 upon h as h tends to 0, that is equal to limit 0 upon h as h tends to 0, that is obviously 0. Similarly, f dash 3 is equal to limit f of 3 plus h minus f of 3 upon h as h tends to 0 can be simplified as limit 3 minus 3 upon h as h tends to 0 is equal to 0. Let us now see a geometrical interpretation of derivative of a function at a point. Look at the monitor. We have a graph here. This is your x axis, this is y axis, and this is the graph of the function y is equal to f of x. Notice the point P as a comma f of a and point Q as a plus h comma f of a plus h. We have a tangent here making angle psi with x axis. So, let y be a function f of x and let P be a comma f of a and Q be a plus h comma f of a plus h be 2 points close to each other on the graph of this function. We know that f dash a is equal to limit f of a plus h minus f of a divided by h as h tends to 0. From the triangle PQR, it is clear that the ratio whose limit we are taking is precisely equal to tan QPR, which is the slope of the chord PQ. In the limiting process, as h tends to 0, the point Q tends to P, and we have limit f of a plus h minus f of a divided by h as h tends to 0 is equal to limit QR upon PR as Q tends to P. This is equivalent to the fact that the chord PQ tends to the tangent at P of the curve y is equal to f of x. Thus, the limit turns out to be equal to the slope of the tangent. Hence, f dash a is equal to tan xi. For a given function f, we can find the derivative at every point. If the derivative exists at every point, it defines a new function called the derivative of f. Formally, we can define derivative of a function as follows. Suppose f is a real valued function. The function defined by limit f of x plus h minus f of x divided by h as h tends to 0, wherever the limit exists is defined to be the derivative of f at x and is denoted by f dash x. This definition of derivative is also called the first principle of derivative. Thus, f dash x is equal to limit f of x plus h minus f of x upon h as h tends to 0. Clearly, the domain of definition of f dash x is wherever the above limit exists. There are different notations for derivative of a function. Sometimes f dash x is denoted by dy dx of f of x, or if y is equal to f of x, it is denoted by dy upon dx. This is referred to as derivative of f of x or y with respect to x. It is also denoted by d of f of x. Further, derivative of f at x is equal to a is denoted by d by dx of f of x at a, or df upon dx at a, or even df upon dx at x is equal to a. Now, let us solve some examples. Find the derivative of f of x is equal to 10x. For the solution, since f dash x is equal to limit f of x plus h minus f of x divided by h as h tends to 0 is equal to limit 10 into x plus h minus 10 into x upon h as h tends to 0 can be simplified as limit 10h upon h as h tends to 0, that is equal to limit 10 as h tends to 0, that is equal to 10. Another example here, find the derivative of f of x is equal to x square. For the solution, we know f dash x is equal to limit f of x plus h minus f of x divided by h as h tends to 0 is equal to limit x plus h whole square minus x square upon h as h tends to 0 can be simplified here by expanding the binomial a plus b whole square is equal to a square plus b square plus 2ab, and then solving it. We have limit h plus 2x as h tends to 0, that is equal to 2x. Look into another example here. Find the derivative of cos x from first principle. For the solution, let f of x is equal to cos x. We have f dash x is equal to limit f of x plus h minus f of x divided by h as h tends to 0 by first principle. That implies f dash x is equal to limit cos of x plus h minus cos x divided by h as h tends to 0 can be written as limit minus 2 sin x plus h plus x upon 2 into sin x plus h minus x upon 2 divided by h as h tends to 0. This we have solved using a formula cos c minus cos d, which is equal to minus 2 sin c plus d upon 2 into sin c minus d upon 2. This can be further simplified as limit minus 2 sin 2x plus h upon 2 into sin h upon 2 upon 2 into h upon 2 as h tends to 0. That is equal to limit minus sin 2x plus h upon 2 into sin h upon 2 divided by h upon 2 as h tends to 0. As we know, limit sin h upon 2 upon h upon 2 as h tends to 0 can be written as 1. The given limit can be simplified as minus sin into 2x upon 2 into 1. That implies f dash x is equal to minus sin x. Now, let us look into one more interesting example here. Find the derivative of the function f of x is equal to 1 upon x cube from first principle. For the solution, we have f dash x is equal to limit h tends to 0 f of x plus h minus f of x divided by h. That implies f dash x is equal to limit 1 upon x plus h whole cube minus 1 upon x cube divided by h as h tends to 0. That is equal to limit x cube minus x plus h whole cube upon x plus h whole cube into x cube into h as h tends to 0. Now, by expanding the cube, we have limit x cube minus x cube plus h cube plus 3 x h into x plus h upon x plus h whole cube into x cube into h as h tends to 0. This is equal to limit minus h cube minus 3 x h into x plus h upon x plus h whole cube into x cube into h as h tends to 0. That is equal to limit minus h into h square plus 3 x into x plus h upon x plus h whole cube into x cube into h. We have taken h common here and you can see h gets cancelled from numerator and denominator, and we can solve this as limit minus of 0 plus 3 x into x plus 0 upon x plus 0 whole cube into x cube as h tends to 0. That is equal to limit minus 3 x square upon x cube into x cube as h tends to 0. That can be further solved as minus 3 upon x to the power 4. Therefore, f dash x is equal to minus 3 upon x raised to 4. Now, students, I hope you must have understood how to find the derivative using first principle. Now, it is time to take down the home assignment. Take down the question. Find the derivative of the following function from first principle. Question number 1, x cube minus 27, 2 x minus 1 into x minus 2. In the next session, we shall continue with the algebra of derivative of functions. Thank you.